This is a video lesson for area under velocity time graphs. The learning target for this lesson is, I am learning to determine the displacement of an object by calculating the area under a velocity time graph. The success criteria for this lesson are, I can understand that the area under an object's velocity time graph is equal to the object's displacement over the corresponding time, and I can determine the displacement of an object by calculating the area under the curve of a velocity time graph. So we can calculate the area under the curve of a velocity time graph to find displacement over time. So we can calculate the area under a velocity time graph in two ways. We can do it using the definition of average acceleration, which is average acceleration is equal to delta x over delta t. And here in this equation here, we've just rearranged the equation to solve for delta x. So we have delta x is equal to the average velocity times delta t. Or we can do it geometrically. And we're going to look at several different examples of that in the next few slides. And we'll also look at an example from an AP question as well. So we're going to start in this example using the mathematical formula. So we're talking about delta x is equal to the average velocity times delta t. So we're talking about average velocity here, and since this graph is in two pieces, so we have these two chunks, we got to do both chunks separately. So our average velocity for this first chunk is 2 meters per second. So we have delta x, we'll call it delta x1, is equal to 2 meters per second times delta t, which is also 2 seconds. So that's 4 meters, is meters per second, and then seconds cancel, so we have 4 meters. And then for delta x2, we have the average velocity here is 6 meters per second times, we have 5 seconds minus 2 seconds, so that's 3 seconds. So that gives us 18 meters. So our total delta x then is going to be 4 meters plus 18 meters for a total of 22 meters. So that's the way to do it mathematically in this case. So here we're going to do it here we're going to solve the problem geometrically. So we're going to find the area of these two sections. So remember, the area of a triangle, the area of a rectangle is base times height. So we have the base of section 1 is 2 seconds, and the height is 2 meters per second. So that gives us an area of 4 meters. And then the area of the second section is going to be equal so the base is 3 seconds times 6 meters per second, which gives us 18 meters. So 18 meters plus 4 meters gives us the total 22 meters, which is what we got in the first way. So you can see the two methods are pretty similar to each other. They look pretty similar. It's just kind of thinking about it in two different ways, but you get the same answer either way. So here's a slightly different case. We've got a changing velocity now. So we're going to do this the mathematical way again. So delta x is equal to the average velocity times delta t. So because you have a changing velocity here, you can find the average for the initial and final velocities. And this only works for constant acceleration only. So if you have a constant slope, basically. So first we're going to find the average of the initial and final velocity. So our final velocity is 5 meters per second. Our initial velocity is 0 meters per second. We're going to take the average of that. There's 2 of those. So that gives us an average velocity of 2.5 meters per second. So if we look at our delta x here, so we have delta x is equal to 2.5 meters per second times our delta t, which is 5. So 2.5 times 5 is equal to, final displacement is 12.5 meters. Okay, so now if we do this geometrically, the area of a triangle is 1/2 times base times height. So our base here is this 5 seconds. So our area is going to be 1/2 times 5 seconds times the height is 5 meters per second. So 5 times 5 is 25, divided by 2 is equal to 12.5 meters. So this area under here, which we just calculated, is 12.5 meters, just as we figured the last time. Okay, we're going to do an example AP problem here using finding the area of a velocity time graph to solve for displacement or the changing position. So in this problem, an engineer measures the velocity of a remote-controlled cart on a straight track at regular time intervals. The data are shown in the graph above, so it's over to the left here. During which of the following time intervals, so we're looking for the following time intervals, did the cart return to its position? So we're looking for where did it go back to its original position at time t equals 0. Okay, and we've got some different ranges of possible times. So we've got this, we've got a velocity time graph, but we need to draw a line of best fit here. So we're going to draw a line of best fit here, and then we've got this line, and then this line of best fit is something like this, and then it goes here. So we're trying to figure out where the cart returns to its original position, which is somewhere over here. So at time equals 0. So what we need to do is figure out how much area is displaced during this first section, and then we're going to figure out how far in the second section it goes to figure out what the second set of time is going to be. Okay, so in this first section, we've got a triangle here. So again, this is a velocity time graph. So the area of the velocity time graph is going to tell us the change in position or the displacement. So this is a triangle. So the area of a triangle is equal to 1/2 base times height. So we have 1/2. Our base is approximately, let's say, 3 seconds. So let's say 3 seconds. And then our height goes up to 1.2 meters per second. So that's 1.5 times 1.2. All right, so it's been displaced about 1.8 meters over this time. All right, now we need to figure out where in this interval we think we've got a similar amount of displacement. So we start at 5, and we just need to find an area of the triangle that's similar. So we're probably talking somewhere around here. So somewhere after this period of time, so somewhere after 7 seconds, the remote control car is going to return to its original position. Not before that point. is it going to return? So we're talking, so it's not going to do 5 to 7 seconds. At about 5 seconds, so between 5 to 7 seconds, it is in the process of returning to its position. So after 7 seconds, is when it's going to return. So the correct answer here is 7 seconds to 10 seconds. Okay, and I just want to mention, because I don't think I've said before, the reason why it's returning at this point, it's returning in this half of the graph, as opposed to, or why it's going somewhere for this half of the graph and it's returning in this half of the graph, is because the velocity here is negative, so it's going back to where it came from in this part of the graph. Here we've got a positive velocity, so it's leaving someplace, and here the negative velocity means it's going back in the direction that it came from, because this is one-dimensional motion. So here it's going somewhere, and here in this section, the second section, it's going back to where it came from. So that's why it's returning in the second section, it's returning to where it came from. All right, so what have we learned in this video? We've learned that the area under a velocity time graph is equal to the displacement during that time period. And we've learned how to calculate the area using two techniques for calculating the area under a velocity time graph. One is using the equation for average velocity, and the other is doing it geometrically. All right, thanks everybody.